Our final video for today deals with discontinuous functions and when we are able to integrate them and when we cannot. The type of discontinuity is what determines whether or not a function is integrable or not. For instance, if we have a function that has a removable discontinuity or a hole, this function can be integrated. For this one, you simply pretend the hole is not there and you proceed like you normally would. Another option would be to locate where the hole is at and treat it as two separate integrals. If it is a jump discontinuity, you simply need to treat the problem as if it were two separate integrals. Integral 1 would be the integral from a to c of whatever the function is, and integral 2 would be from c to b. As you will see later, there is a property using integrals that when you add two integrals that have the same upper limit and lower limit as these two do, then that will give you the integral from a to b of f of x dx. The final possibility is some sort of infinite discontinuity. And the reason why this one does not work is because when you try to take Riemann sums, the Riemann sums never converge to a value. In other words, you won't be able to get a rectangle to have a particular height as you get closer and closer to the asymptote. So, to conclude, removable discontinuities, functions that contain those, are integrable. Jump discontinuities, we can integrate those as well. Infinite discontinuities, we cannot integrate. One note about infinite discontinuities: if the interval that we are trying to integrate over does not contain the discontinuity, then we can still integrate it. So for instance, if we're trying to integrate this particular one that I've drawn from a to b, the interval containing a and b is integrable and does not contain the discontinuity. However, if I were to move b to the other side and draw in another half of my function here, then we would not have a rectangle in this area right here that we could take a limit of and get an integral.